Chapter 5 Electromagnetic Induction 5.1 Current Generation in a Magnetic Field. Let's begin. Different falling speeds. The two orange balls in this demonstration fall at different rates. That's ridiculous, as all things should fall with the acceleration due to gravity. The ball B with a magnet core falls much slower. But why? Note that the tube is made of aluminium, not iron. Aluminium is not ferromagnetic, so the magnet is not attracted by the tube.
Here are two balls of similar size and mass. One of them is embedded with a piece of metal, while the other one is embedded with a piece of magnet. We drop the balls in turn so that they fall freely inside an aluminium tube. Can you tell which ball is embedded with the magnet? Why?
1. Induced EMF and current. You have learned in the last chapter that a current produces a magnetic field. What about the reverse? Faraday discovered that a changing magnetic field can produce a current, and now we call it electromagnetic induction. A. Conductor experiencing a change in magnetic field. Experiment 5A. Relative motion of conductor and magnet. In the following experiment, we will study how a changing magnetic field may induce a current.
This coil has 10 turns. It is connected to a light beam galvanometer. The galvanometer detects a current when its light beam is deflected. Hold a bar magnet stationary near the coil for a while. What happens to the light beam of the galvanometer? Move the magnet into and out of the coil. Is the light beam deflected this time? Now observe how the deflection of the light beam is affected in the following three cases. Firstly, move the magnet faster. Secondly, replace the magnet with a stronger one. Lastly, wind more turns on the coil. This time, hold the bar magnet in position and move the coil instead. Observe if the light beam is deflected. According to the above observation, what can you tell about the conditions for a current to be generated?
So we see that when there is a relative motion between a magnet and a wire, there is an induced current. And the effect is stronger when the motion is faster, the magnet is stronger, or the coil has more number of turns. In fact, when the conductor experiences a change in magnetic field, a voltage is induced. Such a voltage is called induced EMF. The direction of the induced EMF depends on the change in magnetic field. If the conductor is connected in a closed circuit, the induced EMF will then drive a current in the circuit. On the other hand, if there is no relative motion between the conductor and the magnetic field, then there will be no induced EMF and hence no current produced. Lastly, what if there is no closed circuit? There is still an induced EMF. Even though there is no closed circuit, there is no induced current flow. B. Conductor cutting through magnetic field lines. other than relative motion between a conductor and a magnet. Induced EMF is also produced when a conductor gets across a magnetic field. Experiment 5b. Moving a conductor across a steady magnetic field. In this experiment, we are going to move the wire in different directions, such as vertically up and down, forwards and backwards, left and right, and let's find out in which cases there may be induced EMF.
Connect a wire to a light beam galvanometer. Observe the deflection of the light beam in the following 3 cases. Firstly, move the wire vertically up and down between a pair of slab-shaped magnets. Secondly, move the wire forwards and backwards between a pair of slab-shaped magnets. Finally, move the wire left and right between a pair of slab-shaped magnets. According to the above observation, how should the wire be moved in the magnetic field so that an induced current can be produced? Now we will find out how the deflection of the light beam is affected when different changes occur. First, the wire is moved faster. Then stronger magnets are used. Lastly, the wire is wound into a coil with several turns. What do you observe about the deflection of the light beam in the above changes?
The second part of the video confirms our observations that the induced EMF increases with the speed of relative motion, the strength of magnetic field, and also the number of turns of the coil. What about the first part of the video? Between the poles there is magnetic field. We may represent the magnetic field by magnetic field lines, also known as magnetic flats. In order to induce EMF, the wire must move and cut the flux lines. Moving the wire parallel to or in between the field lines do not induce an EMF. In other words, in the above experiment, it's only in the case when the wire is moved perpendicular to the field lines. It may cut the field lines and then induce an EMF. In the other 2 cases, there will be no EMF produced. C. Faraday's law of electromagnetic induction. Now we know that the induced EMF increases with the relative motion between the conductor and the magnetic field. Also, the strength of the magnet, as well as the number of turns of the coil. And this is summed up by Faraday as his law of electromagnetic induction, which described the induced EMF quantitatively in such a relationship that the induced EMF is directly proportional to the rate of change of magnetic field passing through the coil, or the rate at which the conductor cuts through the magnetic field lines, both represented by the same relationship here. But how to measure magnetic field passing through a coil, and how to measure the rate at which the conductor cuts through the magnetic field lines? Anyway, finish the checkpoints below. Let's continue the discussion afterwards.